This is the second part of solving differential equations using direct methods. In this video, I'll be talking about how to solve a nonlinear second-order differential equations where we have the second derivative of y is equal to 2 times the first derivative plus 10 times y squared with two boundary conditions. Again, because we have one boundary on the left at x equals 0, we have y equal 10, and derivative on the right side, on the other side of the boundary, is equal to 0 at x equal 1. So that's why it's called boundary value problem, because we have conditions on both sides of the domain. We already saw the linear version of this before. Now we're going to see what the difference is if we make this nonlinear. So the nonlinearity comes from the second piece on the right side, 10 times y squared, because that is the nonlinear term. Alright, so our method would be the same. We're going to use direct methods. We're going to use central difference to discretize the first piece as before, the second piece again as before, and then for the third term here, or the second on the right, there's no discretization. We just write this as 10 times yi squared. Alright, so this is the discretized form of it. This is the central difference of the second derivative, central difference of the first derivative, and that's the term without derivative. All of them brought to the left side. So here's the equation, and here's the discretized form of it. We group similar terms, starting from yi plus 1 to yi and then yi minus 1. Now you notice that because this is nonlinear differential equation, the equation we get after discretization, like the one we have here in equation 1, is nonlinear. This is the linear term which we had before. This is the nonlinear piece. So you begin to see that we cannot actually solve this anymore using a linear system if you increase index I from let's say 2 to n minus 1. Alright, so now we see that then the nonlinearity comes from the third piece here. Alright, so for the boundary conditions, on the left there's no problem because y is constant. On the right side where we have derivative, we use same backward difference. Alright, so now we have the differential equation discretized in equation 1. Left boundary, let's say y naught is given on the left, and then derivative is equal to something like 0 in this case on the right. So we have three equations. We put all these three into a matrix form. This is very similar to what we did before. There is no difference so far. The only discrepancy is where we assemble the matrix like this, then this becomes nonlinear. Okay, so we cannot use / operator anymore because this is nonlinear. So what we do now is we have to do iterative. We have to use iterative scheme to basically solve for the unknowns, and that's where the Newton's iteration comes in. So this is, let's say, the y vector unknown vector at n plus 1 iteration. This is y vector at nth iteration. This is the inverse of the Jacobian, and this is the function at iteration 1, or at iteration m. So if you forgot how to do this, then go back to Newton's method to solve nonlinear system and see how we can assemble that. So there is nothing specific here. The h, which is the Jacobian, is nothing but the derivative of every equation that we had here for different I values with respect to yj. So if you have, let's say, n minus 1 equations, then we have to take derivative of every equation with respect to yj. And j goes from, again, j goes from 2 to n minus 1 because y1 is known, so y1 is not among the unknown list. Our unknown list starts from y2 to yn minus 1. Or if you will, actually, y2 to yn. Yeah, because when I is n minus 1, then the last unknown is going to be yn. So we have n minus 1 unknown. Anyway, so our Jacobian would be n minus 1 by n minus 1. Okay, so we have to iterate this until we get the y converged, after which we concatenate with the initial condition. So here's the pseudocode for that. We're going to start, let's say, with two. We're going to start with two unknowns. So one thing that I'd like to point out here is, because this is a nonlinear differential equation leading to a nonlinear system of equations, we cannot use back-and-forth operator, and we have to do iterative. We have to follow an iterative approach to find the y. But if you start with, say, n unknowns or n discretized points, and n is, let's say, 100 or 1,000, then basically you have to solve a 1,000 by 1,000 nonlinear system, which is very difficult in Newton's method. So to alleviate that problem and basically approach this, we start from very few unknowns. So instead of discretizing the problem to 100 points, I'm going to start with 2 points, or a handful of them, and then I solve the problem once after my Newton's method converged. Then I increase the number of discretization and solve the problem again using an initial condition, which is coming from the converged solution of the previous step. So let me show you exactly what I mean by that. So we start with, let's say, discretized level of 2, and every discretized level gives me 2 raised to the level plus 1 points. Let's say if discretized level is 2, then 2 raised to the second power plus 1, I get 5 points across my domain. Okay, so from the left to the right side of the domain, I only have 5 points. So I'm not going to have 100 points initially. I'm going to start with 5, given that the level of resolution, I call it discretized level, equal to 2. So over time, I'm going to increase this discretized level to 3, 4, 5, and all the way to the end, however many I want, until I reach the desired accuracy. All right, so let's say with 5 points, I'm going to go and create my unknown list. We call it y old. I have a vector of 5 unknowns. I put 0 in there. The first point is known because that's the left boundary. I set my relative error to 1. I put a tolerance of 10 minus 4, and I want to iterate over the Newton's iteration, or Newton's step, up to 20 steps. All right, so here is the pseudocode for solving the or using Newton's method to solve the nonlinear system and increase the number of points over the steps. So initially, remember, we start from this discretized level of 2 with 5 points. Then my next resolution would be discretized level 3. And when discretized level is 3, so if you put 2 here, 2 plus 1 is 3, then the next level would have 2 raised to the third power plus 1, which is 10 points. I'm sorry, 9 points. So 2 to the third is 8 plus 1 is 9 points. So you see that I go from 5-point discretized domain after convergence to 9. And then let's see if my 9-point discretized domain converges, the next level would be, if I put discretized level equal to 4, so 4 plus 1 is 5, 2 to the 5 is 32, plus 1 is 33. So from 9 point, I'm going to go to 33 points. So you can see that how I increase my discretization over time, or over iteration steps. The reason I'm doing this is because if you have a nonlinear system with, let's say, 1,000 points, and you use Newton's method, the convergence would be really, really slow. So you want to start small. You want to start with very few unknowns. In this case, we started from 5 unknowns, and then we increased the number of discretization over time to get to 1,000. So convergence on 10 unknowns or 5 unknowns would be much, much easier compared to convergence over 1,000 points. That's why we increase the discretization over time. All right. So the rest would be a Newton step. So I'm going to jump to the Newton's iteration, so you can grab this piece from your homework problem from before or from previous lectures. You do the iterations, Newton's iteration on y vector. After you solve it, then you check compared to the relative error. Now your relative error would be the current y minus the old y divided by norm of old y. Now remember, our current y, the dimension of the current y is almost twice compared to the dimension of y old, because the number of points in the current y is almost twice as the number of points in y old. Again, because the number of points in every level, our discretized level, depends on the power here. So from y old to y current, discretized level varies from 2 to 3. Let's say in the first step. Initially it was 2, now we're going to put 3, so we're going to go from 5 points to 9 points. Anyway, so when you do when you calculate the difference in the solution, there has to be you have to subtract 2 vectors of the same dimension. Because this has dimension twice as big, you have to go and pick up every other element in y, in the current y, and then subtract y old from them. Alright, so that's the relative error. You check the relative error every time you iterate until convergence. After you converge, that means the discretized level, the current discretized level is converged, then you then you're going to stop at that discretized level. So if the relative error is bigger than the tolerance, then you're going to increase the number of points within the domain until you reach convergence. At every discretized level, you have to do Newton's iteration to solve the nonlinear system. All right, so now there's an example here that I'm going to go over it, which is very similar to our homework problem. So this is the example we're going to look at. This is another nonlinear differential equations with 2 boundary conditions. Y is equal to 100 on the left side, and then y is equal to 0 on the other side. So in this problem, we do not have derivative boundary conditions. All right, so one point that I want to make here is the number of points goes with the discretized level. If the discretized level is 3, the number of points in the domain would be 9 points. If the discretized level is 4, then we get 17 points. And then we're going to jump to 33 points and so forth. So we're going to increase the number of discretized level, or the resolution of discretization over time. Okay, so I hope this is useful. In the next video, I'll be showing the MATLAB script how to discretize this nonlinear differential equation using central difference. And I'm going to talk about the details of the MATLAB script. So thanks for watching.